Today we are starting off our final unit of this interesting, interesting semester. Year also. So this unit is on astronomy. Now, uh, this unit was originally already going to be a little bit different than the last stuff because I put this unit together before I did it last year, so I sort of made this myself. Um, and so since I had a lot more freedom for it, and also because this is kind of a lot of like extra stuff that's not like strictly in the standards, there are a few things, but it's a little bit different. So because of that, I had more freedom in terms of what I wanted to do and how I wanted to do it. So I originally made this unit with the idea that there's a lot of stuff that we have here that would be more like not just kind of a lecture or like here's some info, blah blah blah. Right? It was more like let's kind of work together to go through a thing and sort of explore things like that, kind of together in a classroom, which we can't really do as well. So I'm going. It's going to be a little bit different in terms of how things go. We'll see exactly sort of how I can transfer things over to an online environment, but hopefully everything sort of works out okay. And so we're going to try that with a lesson for today to start things off. Now, this is a little bit different. There's no warm up or wrap up question. Instead, you just have 6 questions, and they're basically all about here's some images, describe sort of what they are and what they're going for. So today's going to be a little bit of a different thing. And again, I'm kind of using this as a way of sort of thinking about some astronomical stuff. A lot of this, like a lot of background physics stuff, so you might already know about this because we've already kind of gone over it in some detail. But again, you're thinking about it in a bit of a new context and thinking of it in this way. So for the first image we have here, it's this graph here. And in fact, I will here. So here's the full. I can actually make it bigger. There. So here's our full image for the first graph. So what I want you to do is just sort of look at this. Look at all of the detail that's given, look at all the data, and just sort of describe what this seems to show. Think of it in two different ways. First, just the what, exactly what, okay? What is shown in terms of this is that, that is that, here's what's on this image, here's what's on this graph. And then secondly, think about, okay, from this information that's given, what sort of conclusions can I draw from this? Okay, so just think about this for a bit. Again, pause it, think about it, put it together, and write out, a bit to kind of describe it. I'm not expecting you to sort of get this necessarily 100% correct, but just sort of think about it, look at it, and just see if there's anything interesting you can notice about this, and sort of what information this is given to you. And also, you might like, well, I don't know exactly what everything means. Well, try to maybe think about it and figure it out. Okay, so pause this, and then once you have something down, then come back and I'll explain it. Okay, so the very first thing that you might not know is just the very top there, Kepler's planet candidates. Okay, what does that mean? A planet candidate is basically something where, based on data that we have seen, we think, hey, this thing could be a planet, and we're not 100% sure, hence why it's a planet candidate. These are all planets, or planet candidates, around other stars. Okay, so within this time frame, from May 2009 to March 2011, the Kepler Space Telescope was observing a bunch of stars and collecting data on these stars, and from that, they basically found, hey, here are all of these things that could be planets. And then the blue, the red, and the yellow is basically how, as we analyze the data and we get more information to analyze it, how long it took for us to sort of like look into this and say, oh, we think the blue stuff should be planets that we found in 2010, 2011. The red stuff is 2012. The yellow stuff is 2013. Even though all of the data was actually taken in this time frame of 2009 and 2011. So the graph here we have on the x-axis is the orbital period in days, right? And that's how long it takes the planet to orbit its star. This would be in Earth days. And then the radius relative to Earth. Okay, so this in the y-axis is how big the planet is compared to the Earth. Now, there's also, you can see here's these lines here. So if basically a planet that is on this line is the same size as the Earth. Okay, anything less than that is smaller than the Earth. And then also it's depending on how far away it is. So the Earth itself would be like here-ish, about. Again, 200, 400, so 365, so that's about a little bit more than 3/4. So yeah, it's about here. Earth would be right here. Okay. Then up here, we have 4. This is about the size of Neptune. So Neptune, a planet the size of Neptune would be on this line here, and planet the size of Jupiter would be on this line here. And so you can see there's a big range of stuff here, right? We have some that are really, really small. And again, these are all candidates, so it's likely that some of these turned out to actually not be actual planets based on maybe just data fuzz or whatever. So I'm not sure if these really tiny ones are actually planets or not, but you definitely have, I'm sure some of these smaller ones than Earth are actual planets. You have a lot of planets, interestingly, that are between Earth and Neptune, and because there is no planet in the solar system between Earth and Neptune in size, so it's sort of, this sort of in here is a very kind of interesting sort of type of thing to look at, because we don't really know what a lot of these things would be like. Then we have a lot of other gas planets that would be between Neptune and Jupiter. So again, Uranus and Saturn are between those. And then we also have a fair amount of planets that are bigger than Jupiter. So interesting to see from that. Now from this data, one thing to also notice is that by far, most of the planets are quite close to their stars, right? I mean, again, you can see the scale of this is not linear, right? It goes 1, 4, 10, 50, 100, 200, 400. But even then you can just see there's like the most of them are kind of right in here, right? That's where most of them seem to be, and that's definitely, orbital period 4, 10, like that's very, very close. So just because it's the size of Earth, that doesn't mean it like would have life on it, right? Because it could be like right next to its star. So that's definitely something that's interesting. And then also something to notice is that if you just look at the difference between color, so the blue planets, again, those are ones that from the data we could figure out in 2010, 2011, red 2012, and yellow 2013. The yellow ones are mostly down here, where the blue ones are kind of more up here. And so think about how this makes sense, because that means the blue ones, a lot of the blue ones are bigger, whereas the red ones are smaller and the yellow ones are smaller. And that makes sense. The bigger planets are going to be easier to see. Okay, so hence why we could see them early on, and then we needed later years to see the smaller ones. So yeah, that makes sense. Again, it's not perfect, right? We can see some, there's still definitely some very large planets in 2013, but it's something, right? So that's something you can definitely kind of get at from there. So all of that you can kind of use to think about what this describes. So basically, this describes a bunch of exoplanets, which is the term for planets around other stars, observed by Kepler Space Telescope from 2009 to 2011, and they plot them based on how big they are and how far away they are from their stars, and you can kind of see sort of a connection here between that. Okay, second graph. Here. So this is actually very closely related to what we did before, but again, it's just a little bit different information, so think about kind of how this works and try to figure out maybe what the numbers mean because of this. Okay, so this one, again, very similar in terms that we have these different planet sizes, right? And we have them split into 5 different categories. We have planets that are about Earth size, or less, planets that are super Earths. And basically, a super Earth is a planet that we say is bigger than Earth, but we still think it's going to be a rocky planet. Neptune size is like kind of smaller gas giant planets. Jupiter size is, larger gas planets, and then larger than Jupiter is, larger than Jupiter. These numbers here, so if you may remember this from when we did some gravity stuff, this circle with a plus in it, that's the symbol for Earth. So what this means is that anything in this group here is a planet that is less than 1.25 times the radius of Earth. This is 1.25 to 2 times the radius of Earth. This is 2 to 6 times the radius of Earth. This is 6 to 15 times the radius of Earth. And this is over 15 times the radius of Earth. So going back to this first image, by the way, Neptune is almost exactly 4 times the radius of Earth. And Jupiter, I think, is close to 11. I think that's what it is. Anyway, so yeah, that's about the size, how that kind of lines in with there. Now, this basically tells you, okay, again, this is Planet Candidates. This is as of January 7, 2013. Is that kind of what this one says, actually? It doesn't really give a date for that, but you can see, again, you have yellow's 2013. So, again, it's roughly similar thing. And so you can see here, it sort of tells you how much stuff there is. Now, keep in mind, this is not necessarily how many planets there are, but this is how many planets we have seen in general, it's going to be easier to see larger planets. Okay, so there's probably a good amount of Earth size in smaller planets, but it's harder to see them because they're smaller. But again, you can see the most we have are planets that are roughly Neptune size, which we can see in going back to the first one. Again, that was 2 to 6, I think. So that's basically anything that's within like this range on the axis. Like, yeah, that looks pretty accurate. Most of them kind of fall in that group. So it seems to line up with that pretty well. But there's also a good amount of Earth's super Earth ones as well. And again, this is a way of kind of showcasing also kind of how big they are. The yellow numbers, I'm not 100% what the yellow numbers mean. I think that they're basically saying, like, compared to the previous data that we had, like, how much, what percent of the planets that we see are of each category. I think that's what that means. Or it might just be, like, actually, no, it's probably just, okay, so, again, this is as of January 7, 2013. So whenever this image was made beforehand, maybe January 7th, 2012, this is saying, like, how much this number increased. So this -4, it probably means that then, I guess there were planets that there were things that we thought were planets, but then we've looked at them again and we think, oh, actually we were wrong, they're not planets, hence why the -4%. You can see, like, again, the ones that have increased the most are definitely the smaller planets. These have increased the most in terms of, oh, we've seen a lot more smaller planets than bigger ones, and that makes sense because our technology gets better, we can see smaller and smaller planets. So, yeah, similar kind of thing with that there. All right, our third graph, also similarly related to this kind of stuff, I believe. Yeah, so this one, again, similar kind of thing. See if you can kind of piece things together, figure out what it's about, and any other information you can kind of get from this. Try to think also, because you might think, hey, this seems just very similar to previous stuff. True, but there are some differences here. So try to highlight what is the kind of the difference between stuff that might show up on this graph versus the other two that we've seen so far. Okay, so this is very similar to the first graph, right? The first graph had the orbital period in days and the radius of the planet relative to Earth. This has the semi-major axis in AU and the planet mass. I think this is also relative to Earth. I think so. This is mass of Jupiter. Okay, this is relative to mass of Jupiter. So, another thing to note, though, is also that the last graph, again, this is 2013 stuff going up to here. This, though, 2007. Okay, this is January 29th, 2007. Right? Remember, Europe writes their dates, day, month, year. So this is a while ago. So this is when this stuff kind of not just started, but it was still in its early stages. So here we could really just see, like, the biggest planets, right? The Jupiter ones. And we have planets here that have a mass that's like over 18 times the mass of Jupiter. Like, these are huge planets. Okay. Now again, mass scales differently from radius. These planets are not like 18 times larger in radius than Jupiter, but there's definitely bigger. So Jupiter itself would be, where would Jupiter itself fall into this? It would fall into this about, is its AU, I think is it like 5? I think it's like 5. So I think Jupiter would be about here-ish if it was on this graph. So yeah. So you can see, again, like, a lot of these planets, first of all, again, there are some very big ones, but most of them are close-ish to Jupiter, which, again, makes sense. There's probably not going to be a lot of totally enormous planets. But notice there's a lot of them that are very close to their stars, right? Less than 1 AU, right? Earth is 1 AU, right? So Earth is here, and of course it's way smaller than Jupiter, so it's like, really close to the axis here. But there's a lot of, so basically you're saying there's a lot of planets that are about the size of Jupiter that are, like, where Earth is, and there's a lot that are even closer, right? And so I believe, actually, the very first exoplanet we found was bigger than Jupiter, and it orbited its star in, like, 4 days, or something ridiculous. So it was incredibly close to its star, and there's a bunch of stuff like that that's really strange, and there's kind of, it's this term for, it's called hot Jupiters, where they're these planets that are the size of Jupiter, but they're, like, again, very close to their stars, and they're incredibly hot. And so it's one of the, and based on what most predictions are for how our solar system formed, we think that like shouldn't really happen. Um, because you may notice, hey, all the rocky planets are closer in, all the gas planets are further out. We think there's a reason for that because the rocks, the gas is much easier to spread out, and it would be further away. It would be affected by gravity less, so it would kind of fall. It would kind of move away from the star, whereas the rocks would be pulled into the star. So the fact that we have these really giant gassy planets near stars is weird. The most common hypothesis is just that sure they formed out, they maybe formed out where like Jupiter and Saturn are now, but then they ended up somehow getting pushed inward, either by colliding with stuff or just general gravity mess ups or whatever. Um, but that's kind of the question. And granted, for stuff like this, because how many bajillions of stars are there, right? So even if there's like 1,000 stars that have these hot Jupiters, that's like that's still something that's a very small minority, but of stars. But it's still something that like we don't fully understand how it works, and we don't understand how common it is, right? Because we've only seen so much stuff, and these kind of things are very easy to see, right? Hot Jupiters are one of the easiest planets to see because they're very big and they're very close to their stars. So it in the different ways that we can track exoplanets, which we'll go over this later. Those two things are the easiest things to see. Larger and closer to the star are the most easy things to see, which just sort of kind of conceptually makes sense, even if you don't know the actual method for doing it. So these are the planets we would find first. So if anything, the data that we have is these kind of planets are oversampled. We see more of these than there actually are if we were to find every single planet. So, anyway. Okay, so those are the three that are about kind of planets around other stars. The next are things that are more related to sort of our solar system itself. So, image 4. Okay, so this is not related to planets around other stars. This one, it's kind of a lot to look at, but it's not that complicated in terms of what it's actually showing if you just kind of sit back and look at it for a moment. So just think about this for a bit and try to also notice any interesting patterns you can get. Okay, so first of all, what does the top say at the top here? Jupiter moon's orbit graph for September 1998. 1 Io, 2 Europa, 3 Ganymede, 4 Callisto. So these 4 moons are 4 of Jupiter's moons. They're known as the Galilean moons because Galileo actually saw them with his telescopes. And these are the 4 biggest moons around Jupiter. And it's sort of tracking their orbits around Jupiter. So on the x-axis is the day of the month. Okay, so I guess, let's see, it's September. Okay, it's the 28th, so this would be 27, 29, right? Because then 30 and then 1. Yeah, September's 30 days. So, tracking where they are. And then, so here, this is W, this is E. So the question is, okay, what does this mean? It's west-east. That's actually all it is. So just think about this. Basically, if you were to stare at them in the sky compared to where Jupiter is, for example, let's follow blue. That's 3, so that's Ganymede. So this basically saying, okay, as you track Ganymede across the sky, it goes to the west, and then it ends up going back to the east, and then it goes to the west, and then to the east, and then to the west, then to the east, then to the west, and the east. It goes basically west-east compared to Jupiter. So these sine waves, which is what these all are, these are basically tracing the orbital paths of the moons, but just from our perspective looking at them, right? You'll notice the pattern here is that, for example, 1, Io, that's the one that not only is the quickest of moving back and forth, right? It's, the period of the sine wave is really, the wavelength, if you want to think of it that way, is short, but also the amplitude is also the shortest, right? And this makes sense. So this is saying since the amplitude of the wave is small, that's saying the actual amount that it moves west and east is small, which means it's going to be pretty close to Jupiter. It's kind of orbiting around it in a pretty small motion. And that's taking it, and that because it's orbiting in a small motion, it's doing that fairly quickly. Compared to Callisto, number 4, that's orbiting at a much larger distance, so it's orbiting further away, and that means also the period is slower. So because it's orbiting far away, it's orbiting slower. So that's kind of what it's getting at. So Io is the closest moon of these 4, so it's orbiting quickly. Next is Europa, which is a little bit further away, but it's still orbiting pretty quickly. Then Ganymede, it's orbiting further away, orbiting a bit slower, and then Callisto is furthest away, and it's orbiting the slowest. So kind of seeing how that works from that there. And you can see this lines up, these sine waves line up quite well. So, yeah. Fifth image. This one's kind of hard to see because it's not. If you can zoom this in a bit. Ugh, quality's not good. You can probably read that mostly, hopefully. So just see kind of what this shows and what you can get from this. There's kind of a lot to look at here, so give it a moment. All right, so as the top of the graph says, the relative masses of the heaviest solar system objects. So basically, they're taking how many objects is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 30, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 45, 46, 47? Might have miscounted, but I counted 47 of the heaviest objects in the solar system, and just plotted them on this graph. So what does the graph show? The y-axis doesn't show anything. Okay, so the y-axis is just sort of a way of ordering them. The x-axis, though, shows relative mass where Earth equals 1. Okay, the e term here, this is sort of your exponential. So 1e0 is basically 1 times 10 to the 0. Okay, so in other words, just 1. So on this line is Earth, the mass of Earth, which, yeah, there it is. And then you can see 1e1 is 1 times 10 to the 1, which is just 10. So basically a planet would be exactly 10 times the mass of the Earth. Here, 1e2 is something that's exactly 100 times the mass of the Earth. This is 1,000 times, 10,000, 100,000, and 1,000,000 times. And so here, of course, we have the sun as, like this is a logarithmic scale, so this is probably about like 300,000 times the mass of the Earth, something like that. So definitely the biggest in terms of mass. Then we have Jupiter, that's about, again, it's about, I think, 300 times the mass of the Earth. Saturn's about 100 times the mass of the Earth. Neptune and Uranus, I think, are like about 16, 14 times the mass of the Earth, I think. And then Earth is 1. Venus is a little bit less. I think it's like 80, 90% of the Earth's mass, something like that. Mars, yeah, is about 1/10 of the mass of the Earth. Mercury is about like 4 or 5%, I think, the mass of the Earth. Over here it says blue marker indicates satellites. That's moon, right? Satellite is moon. So here's several. Again, here's some of the moons we just looked at: Ganymede, Callisto, Io, and Europa, all in here. These are moons of Jupiter. Titan is the moon of Saturn, so that's the second biggest moon. And then here we have our own moon. So our own moon is the 5th biggest moon. So that's a pretty big moon. And also, I've said this before, I believe, but our moon is the biggest compared to its planet. Okay? Because Ganymede, Titan, Callisto, and Io are bigger, but they orbit, Jupiter and Saturn. They're way bigger planets. So in terms of like the ratio of moon to planet, our moon is the biggest. So that's something that's kind of interesting. By quite a lot, actually. And then Europa. Triton is a moon that orbits Neptune, so it's pretty large. So now back to red. Eris and Pluto. So Eris and Pluto are not planets. Eris and Pluto are dwarf planets. And again, this is sort of thing is like why is Pluto not a planet anymore? Because if Pluto was a planet, Eris would have to be a planet, because it is as planety as Pluto is. And there's also other things as well. For example, Haumea, Sedna, Quaoar, how do you pronounce this? Ceres, Orcus, Varuna, whatever this is. I think these two are actually considered asteroids. I'm not sure. Anyway, there's definitely some more to this in there. Anyway, so all of those have to be considered planets as well, and those kind of things are called dwarf planets, and there's like hundreds of them. So if you basically either we have 8 planets and Pluto is taken off, or we have like hundreds. So that's why, yeah. Let's see, you have some other Titania and Oberon. Those orbit Uranus. Sedna again is another. Sedna, Haumea, and dwarf planets. Rhea orbits Saturn, I think. Iapetus, I believe, orbits Saturn. Charon is a quote-unquote moon of Pluto. I say that as a quote-unquote because, like, it's again, I said how, the moon is the biggest compared to its planet. When Pluto was considered a planet, Charon was the biggest, because Charon's like 2/3 the size of Pluto. It's really big. So, if anything, a lot of people like to argue that, like, Charon is not a moon of Pluto, but instead it's like Charon and Pluto are like both dwarf planets that like orbit each other. That's kind of one thing that they've kind of talked about for that. That's again how you go. There's Ariel and Umbriel. Those are both orbiting Uranus. Dione, I think, is Saturn's moon. Ceres is it's a dwarf planet that's actually in the asteroid belt. So all of the other ones on here, Orcus, Quaoar, Sedna, Haumea, Eris, and Pluto, those are all like out past Neptune. But Ceres is in the asteroid belt. Orcus is out past Pluto. Tethys, I'm not sure where that is exactly. If it's orbiting, where that's orbiting, so I'm not sure about that. Varuna is another one that's out there. You may notice also once you get in here, you get some of these that are squares and some of these that are circles. The circles are things that are actually spherical. Okay, so all of these are spherical bodies. Once you get down to about here, then it starts to be a little bit, there's a bit of a part here where it's like kind of a mix. And I think this kind of comes down to like, just collisions and other stuff. For example, Vesta is an asteroid that's in the asteroid belt. It is not spherical. It's kind of close. Like it looks sort of like a it's potato-ish, but it's like it does look roundish, but it definitely is not a sphere. There's this thing, which I don't even know what this thing is. Pallas, I think, is also an asteroid. I think it's also something. This one, it says it's a sphere. I don't think it's a sphere though. It's. I think it's also kind of like Vesta, where it's close, but I'm not 100% sure. Enceladus is a moon of Saturn. That is a sphere. Hygeia, I guess, is an asteroid, but I'm not sure. I can't read this. Interamnia? I don't know what that is. Miranda, that's a moon of Uranus. Proteus is a moon of Neptune. It's one that it's another one that it's close to being a sphere, but not quite. This is something Europa. It must be some asteroid. I don't think this would be related to the actual moon Europa up there. Mimas is a moon of Saturn. It's the one that looks like the Death Star, if you ever Google it. It is the smallest spherical object, basically, that we've seen. So that's sort of the smallest one. And everything past that are all... they're definitely not spherical. Nereid, I think that's a moon of Neptune? I might be wrong. The others, I guess, are all asteroids. I know Juno's an asteroid. So, yeah. These are all sort of your things that are in the solar system based on mass. And anyways, of course, a lot of stuff up here. And there's in terms of the moons after Mimas, all the ones going down, again, they're all not spherical. And most of them are like not even close. They literally just look like asteroids. They just happen to be orbiting, planets. And there's like, how many moons are there? There's something ridiculous. Like Jupiter and Saturn both have like 70. Neptune, I think, is like 12. I think Uranus is like 20. Then Mars is 2, and then we have 1. So whatever that ends up adding up to. Yeah. Okay. Next up, is this 4 or 5? 5. Okay. So, last graph then, graph 6. See if you might be able to recognize this and what this shows. This is one that we've actually kind of looked at before. So I want to see if you can figure out what it is. Okay. All right. So this is one that you may recognize the shape and you may recognize some of the terms here, but you probably don't know everything. Some of this, actually, I'm not even sure what it means. For example, I have no idea what this call thing is, and I don't know... I know what that is. It's not call, it's calcium 2. Okay. That's what that's saying. Anyway, but this... Okay, so what are these things up here? So, this RA and dec, this is right ascension and declination. Basically, these are coordinates of, like, the sky. Okay, so just like how we have latitude and longitude, we have a similar thing for finding coordinates in the sky. Declination is basically sky latitude, and right ascension is basically sky longitude. Okay, the coordinate system, though, is very confusing because, of course, the Earth is turning and also moving around the sun, so where things are in the sky is constantly changing. So we have a way of, like, standardizing it so that the coordinate system is not like moving with the Earth, but because that it's like really complicated to like learn where everything is. So the main thing is that declination is, since it's negative, it's like below the equator. Right ascension, again, like I don't remember what because just how like we have what's zero longitude, like Greenwich, England. Why? Because, right? Like it's a similar thing here where zero latitude is or zero right ascension is somewhere. I don't remember where that is. It's not. An easy thing would just be like the galactic center, but it's not that. So I don't know. I don't know what it is. I don't know what this is actually. I don't know what these three are. I assume the fiber and the plate has to do with like the kind of actual technology used to do this, but I'm not sure what the MGD is. Anyway, this graph is the blackbody radiation curve that we looked at before, right? So here's sort of your kind of increase, there's your peak, and then there's your steady decrease. But you'll notice there's these big dips in the graph. And remember, how do you get sort of pieces of light taken out of something? It's from the atomic spectra. And that's sort of what this is showing. So this is showing a bunch of atomic spectra lines. And it's sort of labeled them too. So then there's H, let's see, that's H beta. Here's H alpha over here. H beta, I think that's H gamma right there. It's hard to see. And that's H delta. And that's Eta? It looks like Eta, but whatever. Okay. And here you have wavelength down here. This would be in angstroms. And an angstrom is it's 10 to the minus 10. So 1,000 angstroms. No, 10,000 angstroms is a micrometer. So remember wavelength of visible light was like 400 to 750 nanometers? Would be 4,000 to 7,500 angstroms. So that red hydrogen light, if you remember that's this H alpha, which is here. That's this one. So that lines up with, the 600, like 70, whatever it is, nanometers. That's your kind of your deep red from hydrogen. But we also have, I'm not sure. Okay, so N2, that's Li. Nitrogen lithium? Is that a thing? I don't remember that. Anyway, nitrogen sulfur. These are oxygen. I'm pretty sure the Roman numeral is sort of like how just like H alpha and H beta. I think it's related to that. So, but I'm not exactly sure how this all works. What the labeling is. So, but there's oxygen lines. You can't really see the oxygen lines though, but you can see definitely there's a sodium line. You can see that one. Magnesium, you can definitely see that drop there. G. What's G? Don't even know of a element that's just G. Helium somewhere. I guess that's one of these things. Potassium, another one of these things. And these would be calcium. That's what it is. That was like call. Okay, it's calcium. So again, this is showing the spectra of a star. This is not the sun. I wouldn't think so, because again, it would probably just say sun. This is some other star that is at this coordinate position in the sky. This might be a distance thing for the star. I don't know. Anyway, what we do. Oh, so also, if you're wondering, what is the Z thing? Like Z is minus, minus that to plus or minus this. What does this mean? Z has to do with how far away the star is. So remember when we talked about how redshift and blueshift and how like everything sort of seems to be moving away from us once you sort of get out of our local galactic cluster. And how I said that like based on how much the light is being redshifted, you can know how fast something's moving away, and then from that you can figure out like actually how far away it is. That's what this Z number actually is. So Z is sort of a scaling factor with how far away stuff is. So the fact that it's saying like it's plus or minus, like you have this really small range of like, I think it's basically saying I'm not sure, it says it's minus 0.001 plus or minus 0.0. I think it's supposed to be saying that like the Z is either between negative 0.0001 or positive 0.0001. So basically zero. That means it's close, right? So a Z of zero, it's weird to say, is something that's very close to us. So, well, on a galactic scale, right? So, yeah. And I think this is 1.0. I think that's comparative mass. I'm not sure. Compared to the sun, I don't know. So again, this is not the greatest graph in terms of getting information, but this is just another example of the atomic spectra that you've seen before and sort of how that kind of comes together. So hopefully you can kind of like at least get some interesting information from this and just sort of see some patterns. We're going to be covering a lot of stuff here. pretty much everything that we talked about to some degree with these graphs we'll be covering. Well, we kind of already covered this kind of thing with the black body radiation, the atomic spectra, but we're going to see how these graphs are different for different stars. And so that's actually the first thing we're going to get into tomorrow. So we're going to get into tomorrow is another graph. And this graph is, I would say, has maybe the most information of any like widely used scientific graph that I know. There's a lot of information in it, and it's very important because it covers a lot of stuff. So, and that covers basically all different types of stars. So that's what we're going to get into tomorrow. The different types of stars, how they're organized, how they're classified, all that kind of stuff. And sort of the graph that comes with that. So that's sort of also why I was sort of doing this with you now, because sure, there's kind of a lot of scattered information. But tomorrow we're really going to focus on interpreting this graph and what it shows from it. And that's, you can get a lot from it. So that's really getting into tomorrow. And yeah, I guess that's it for me with this one. So yeah. Cool beans.